Okay, so hello everyone, my name is LaBonia. My contemporary issue presentation is going to be on improving CO2 capture through absorption tower technology, and let's get right into it. So the way I'm going to organize this is that first I'm going to tell you why we're doing this, who we're doing it for, and how we're going to do it, and then summarize the advantages of doing this in the future. So first we're going to start with why we're doing this. So the reason why I want to do this is that millions of tons of CO2 are released into the atmosphere each year, and it's becoming more and more because as population's increasing, more people are going to be using power. So this issue is only going to be getting worse, and we have to find solutions or switch to sustainable energy, which is currently in development right now. So it's not the preferred option yet, but we're trying to make fossil fuel energy more sustainable, I guess you can say. And also outside of just like helping the environment by doing this, there's also potential revenue you can be made, which I will go into near the end of this presentation and show you how that's possible. So right here is just some data I'd like to start out with, just showing why also we want to look at this capture technology for CO2. So as you can see here on your x-axis, it shows years ranging, it says 1751, but I don't believe they really have data for that. So really we're only going to look from about 1900 to 2014. And as you can see on your y-axis, it shows MT is million of tons of CO2 produced annually, and this is a global wide scale. So right here you have all your countries listed, ranging from India, China, United States. And as you can see, United States way far outreaches all the other countries by far. So it's even more of an issue of why we should take the step-up advantage in creating technology to absorb CO2 for this purpose. This is another schematic that shows the ppm, which stands for parts per million, of CO2 in our atmosphere. It ranges from 1980 to 2016. As you can see, over the span of about 30 years, we can see we increased our ppm by about 60 ppm average. And now this is like a global scale. So even though 60 ppm doesn't sound like a lot, that's a global scale for the whole world, and 60 ppm is a quite considerable amount. And again, that's just more data showing why we need to take a step in advantage in doing this. So next we're going on to who this project is going to be done by and who would it be for. So this is going to be funded by the U.S. Department of Energy. That's a subsection of the U.S. government that's in charge of creating economically, environmentally sustainable technology. And through the Department of Energy, they are actually funding something called the National Carbon Capture Center, which is located in Alabama. And what they do is they're actually a facility that creates and implements new and upcoming technology to actually explore different ways to absorb CO2. And again, they're very heavily research-based because the technology that exists now isn't good enough to be economically viable. So that's why very little companies actually have carbon capture towers. I believe only one in China does, but on a global scale, very, very few considered. If you look at the whole wide range of carbon of CO2 that's emitted, it's a very small percentage. So the how. So this is going to explain how we actually go across the process of absorbing the CO2. So the way it's going to work is on our left we have, it's called a path column. The way it works is it's just either it could be made of glass, could be made of stainless steel, it could be made of any non-corrosive material. And at the top you have your liquid, or called solvent alternatively, that sprays in from the top. And then you have your gas inlet, where it's gas that comes up from the bottom. And the way it's going to work is they're going to run counter-currently with each other. And so let me go a little bit into the actual interaction between the gas and the liquid. So you can see right here, this is called a random packing material, shown in purple. The actual specific one here is called a Rosteg ring, and what it is, it's a ceramic little cylinder. And what its main purpose is that it slows the interaction between the liquid and the gas, so there can be more mass transfer involved between the two substances. And it actually is more demonstrated down here in this picture, where blue is solvent and red is the gas, which is a mixture of just air, CO2, and other constituents. As you can see, what happens is the liquid actually goes around the purple packing, and it slows its flow rate down considerably, so that allows more time for the gas to interact with it. And as you can see in the diagram on our right, we have a gas phase shown in pink and the solvent phase shown in blue. And this actually occurs right here. This is just a blunt image of really what happens at this point. The yellow circles are the CO2 molecules. What happens is nature wants energy to be at its lowest amount possible. It wants equilibrium everywhere. So if you have something of a high concentration, something of a low concentration, it will actually, the high concentration will diffuse into the lower concentration, which is shown here. And this was taught to us in our courses, like especially in physical chemistry and orgo, etc., that there's going to be a actual physical presence movement of the particles into the solvent phase. So that's actually the main thermodynamic principle of how this reaction occurs. So this is the reaction itself. So there are many different types of reactants of chemicals you can use. The most common ones are amines, because amine compounds are very, very reactive compared to others. You can also use sodium hydroxide as a solvent. You can use bicarbonates as a solvent. You can use ionic liquid as a solvent. But right now in industry, what's currently being researched is MEA. And so this reaction here actually shows how MEA reacts with CO2. So as you can see right here, we have our MEA compound in our CO2, and what's going to happen is the CO2 is going to interact, and this CO2 molecule is actually going to stick itself right here and form this compound right here, which is called a Zwitter ion. And what that means is that's just an intermediate ion that's formed in this reaction. And then as the reaction continues on, this Zwitter ion will actually form a carbamate. And what happens is a proton leaves the nitrogen and it forms its final compound, which has CO2 attached to it. Now that carbamate can actually be reversed back to MEA if you heat it up, because gas solubility greatly decreases at higher temperatures. So the carbamate itself, shown in the yellow dashed lines, will actually reverse back to MEA and release CO2 gas. I'll explain what's the purpose and why you want to do that in the next slide. A side reaction that goes on is I actually have CO2 interacting with water, shown here. And that will form a carbamate compound. It's a very low reaction potential for that to happen, because CO2 doesn't really want to dissolve in water that readily. But it's also another method of how CO2 gets captured. So this is a process flow diagram showing how this process actually works. So on our left, shown at step 1, we have our absorption column. Again, these little cylinders are packed material that slows the flow rate between the gas and the liquid. Again, your gas goes in at the bottom, your liquid comes in at the top, and they counteract with each other. Once the solvent absorbs the CO2 from the gas, it exits here, and the clean gas exits here. And then the solvent actually goes to a heat exchanger. As mentioned previously, gas solubility decreases at higher temperatures. So your heat exchanger actually will heat up the solvent and send it to a stripper column. Now the stripper column is actually going to allow the heated solvent to interact with air, and the air will take that CO2 and combine it with itself, and you can use that CO2 commodity in different types of processes, which will be explained later on. So when will all this really happen? Presently it's not really implemented that well. It's funded by the DOE. However, it's very expensive, which is why the DOE is trying to come up with different methods to actually make this a better process. For the future, it's also, we want it to be very inexpensive, hence that's the goal of this, and more efficient. And we want to use this captured CO2 for different processes. So one, we can use captured CO2 as a pure product for a commodity. Like companies like Airgas can sell CO2, like universities and things like that. So you can actually make a profit from selling just the pure CO2. But really, you can make a profit from selling algae. So algae thrives off carbamates, which can be formed from CO2 as shown previously. And then you can actually grow that algae, and that algae can be used to create different types of biomass and different types of products. And that biomass can be converted into different types of chemicals like biofuels, glycerol, etc. And so that can actually act as another source of energy from energy. And so with that, that is my presentation. I hope you all understand that a better insight of why we need to capture CO2 and how we can go about capturing it, and that it's a really upcoming technology that we can really use to improve our society. And with that, any questions, and thank you.